All right, so how you guys doing today? Good, perfect. So you guys know we have exam next week, so we'll continue on another brief session today. So here's a question I might ask you in the exam here. So you have a organic compound. That shows the 47.3% carbon and 10.5% hydrogen, and then 42.2% oxygen by mass. Okay. So if you have this information, you have 47.3% carbon, 10.5% hydrogen, 42.2% oxygen in this compound by mass. What might be the empirical formula? That's the question. Okay, so I'll give you about 2 or 3 minutes, and then we can do this together. So I want you to try it first, and then we can do this together. So you have organic compounds that is 47.3% carbon, 10.5% hydrogen, and 42.2% oxygen biomass. Okay? And what might be the empirical formula of this compound? That's the question. Maybe 2 minutes. Okay, 1 minute maybe. Could you actually sit and could you sit actually in another chair? Okay. All right, so let's do this together. So if you have those numbers in percentile units over here, so the one easy way to calculate those numbers of each is consider this compound that we have about 100 grams in total. Okay, so then that will be same as, you can say if you have 100 grams of this one, that is the same as what? That's the same as, you can say you have 47.3 grams of carbons. You have a 10.5 grams of hydrogen, 42.2 grams of oxygen, right? If you assume there's 100 grams of the organic compound, because it's a percentile unit as a whole, it should be 100%. So that will be same as this numbers in grams as well, if you have 100 grams of that. Makes sense, right? Okay. So whenever you do this, is the try to find the number of moles. Okay. Let's try to find the number of moles. So if you try to do 47.3 grams, and to get the moles, you can just simply divide that by atomic mass of carbon. Okay, so maybe you can do 12 grams per mole. Okay, so if you do this one over here, you will get about number in moles here, because it's denominator of denominator, so you get number in moles here. And then there should be about 3.94 moles, okay? And then this one same, so we're gonna do 10.5 grams over, it's about 1 gram per mole. This is carbon, this is hydrogen. And you can get, you know, over here, okay? And then we do 42.2 grams divided by atomic mass of oxygen, which is 16, about 16, right? The 16 gram per mole. Okay, that is about 2.63 moles. Okay. Okay. So here's the thing. Whenever you have those numbers in moles now, this is still not so perfect here. Okay. You see, over here, right? And then what you can do is try to find the lowest number, which is this one. Okay, and try to divide these two numbers by the lowest number among those three. Okay, so what I'm gonna do now here is I'm gonna divide this number 10.5 over 2.63. It should be about 4. It's a 3.99 something. Okay, and then if you do this one as well, 3.94 divided by 2.63, that will be about 1.49 something. Okay? So what you can find out here is the ratio. So if you have see, this is 4, right? So this is the same as, this means that this is the same as 4 is the same as what? 4 over 1. Okay, this is the same as 4 over 1, and this one is the same as what? Almost 3 over 2. Okay, so that tells the ratio between these two. Okay, so that is numbers of what? So this was moles of hydrogen. That was moles of oxygen, right? And this is moles of carbon. This is moles of oxygen here. Okay, so see, hydrogen, oxygen, carbon, oxygen. So you have 4 to 1 to hydrogen to oxygen here, and you have 3 to 2 from carbon to oxygen over here. So you have 4 to 1, that is hydrogen to oxygen. 3 to 2, that is carbon to oxygen here. Make sense, right? Okay, so means whenever you have 3 carbons, there will be 2 oxygen. That's what it means. It's a ratio. Whenever you have 4 hydrogen, there will be 1 oxygen over there. Okay, so try to make it more simple integers number. So if you do this one, see, this one is a 3 to 2. It looks okay, but whenever you have 2 oxygen here, how many hydrogen will be there? I mean, when it's 4 to 1. If there's a 2, there will be 8. Perfect. Okay. What do you have now here? So when you fix this number of oxygen as 2, not 1, you can get 8 to the 2 and 2 to 3 here. So we finally have empirical formula, which is carbon 3, hydrogen 8, O2. So it'll be carbon 3, hydrogen 8, O2. That's the answer. Yeah.
Can you repeat that last step one more time?
Oh yeah. So whenever you divide the actual mass by atomic mass, you get the moles of that element, and then you choose the lowest number and try to divide those 2 other numbers in moles, and then to make these 2 together, this is not 1 to 3. It's a 2 to 3, right? So you want to know if there's 2, how many hydrogen will be there. So I doubled those 2 because it's not 1 to 3. If it was 1 to 3, it could have been just 1, 2, 1, 3, 4. But it's 2 to 3, so it'd be 2, 3, and 8, not 4. Because it'd be 2 to 8 if it would have been 2 of oxygen. So we have a 2, 8, and 3 is the answer. Because you don't want to say carbon 1.5, hydrogen 4. Oh, that would be a little bit weird because the 1.5 indicating you're splitting the carbon, which is impossible as definition of what? Atom. Atom cannot be split. Atom itself is the minimum unit of the carbon. Okay. Make sense, right? Oh yeah, sure. Okay. So if I go the other way. Maybe I can try carbon 2. Something like this. So maybe we can go the other way. Okay. So let's try this one first. Okay. So let's try this one first. So we find this one over here. There's one more question I want to ask you. So let's do this first. Okay. So whenever you do this one here, you have an answer for empirical formula. Okay. Then I'll give you actual molecular weight of the compound. Because as you know, this is not molecular formula yet. This is empirical formula that only can be found by mass composition information there. So if you know the actual molecular weight, you can actually find out the molecular formula, which I'll give you about 123 gram per mole was the molecular weight of the compound. Can you guys find the molecular weight? Molecular formula of this empirical formula compound? I'll give you about 2 minutes. And then let's do one more.
So we're like working backwards?
Oh, no, not yet. So I want to do one more from the empirical formula. So try to find out the molecular formula first by using molecular weight. Okay? Because this is the empirical formula we find here, not the molecular formula yet. Only thing you can find out from the mass composition data is the empirical formula, or sometimes molecular, but you can't be 100% sure when you look at the numbers of molecular weight. I'll give you about 2 minutes. Okay, 1 minute. Okay, so what do you guys think? What might be the answer? Would be C. Perfect. 6. It's perfect. O for perfect. Great. So you guys see this? What we just did is just double each numbers on the elements in the compound. Because if you do this one over here, this is the 3 times 12 carbon, 1 times A, which is A, and 16 times 2 is 32, right? So if you do that with 36 plus 8 plus 32, okay? So it would be 6, the 6, okay? Oh no, 7. 76, right? Yeah, 76. Okay. So I thought it was 18 here because okay, anyway, 16. So when you look at this one here, you can try to divide this number by your empirical formula weight. That would be 76. Okay, and that is 2. So technically speaking, in molecular formula wise, you have double amount of each in the formula. It's the empirical formula itself, its definition is the what? Minimum, simplest numbers of each in the chemical elements in the compounds in the empirical formula. So if you just double those numbers in the empirical formula, you can get the molecular formula, which will tell you actual numbers of elements in the one compound. Okay? Does it make sense? Okay. Oh, good. Perfect. So let's do one more example. It makes sense, right? Makes sense, okay.
So in order to find the molecular formula, you always double?
Not always double, because we double this one because your measured molecular weight was the 152, and then when you try to get all the atomic mass times by that numbers in the empirical formula was 76. So when we divide that number by that was 2. So we know, empirical formula only indicates the half of what it has in the molecular formula. So we doubled it. So for example, when you do the empirical formula calculation, it was exactly the same. Then its empirical formula is indeed the same as molecular formula. So you already got the molecular formula by getting the empirical formula, which is even better. Makes sense, right? Perfect. All right, so then let's do one more. So you had compounds made of carbon and hydrogen. Okay, compound and hydrogen. Okay, and the carbon was 75% by mass, and this is 25% by mass. Okay. And what might be the empirical formula of this one? This compound. Formula of compound. Okay, about 2 or 3 minutes. Okay. Okay. Okay, maybe one more minute. Okay, so let's do this together. So once again, I'm gonna assume that this is all, this compound is about 100 grams. Okay, and then this will make this one same as carbon is 75 grams, and the hydrogen is 25 grams over here. Okay. And I'll do the same. I'm gonna divide those two by its atomic mass of carbon and hydrogen, which is about 12 grams per mole. This is about 1 gram per mole. Okay. So obviously this is just the 25 moles. Okay. This will be what? 6.25, right? So if you just do this one, it's 1:4 ratio. Okay. So we know now is what? Methane. CH4. There you go. That's it. You just divide 25 by 6.25. That's 4. So it will be ratio will be 4:1, 1:4. So 1 carbon, 4 hydrogen. Make sense, right? Yeah. Huh?
It was just thumbs up.
Oh, perfect. Perfect. Thank you. So let's move on. Perfect. Okay, the next question was, oh, so whenever you have a 508 grams of sodium bicarbonate, how many moles of compound you have? That's it. I'll give you about 1 or 2 minutes. It should be, yeah, it should be 1 or 2 minutes. Yeah, 1 or 2 minutes. So you have 508 grams of sodium bicarbonate. How many moles of the compound do you have over there? That's the question. So try to get the formula weight, okay, over there, and then divide this number by formula weight over there. Okay, about 1 minute. So the periodic table will be given. Don't worry about the atomic mass. It will be all given on the periodic table. Only thing you have to do is just add all the numbers on here to get the formula weight. That's it. And then divide this number by formula weight. That's the answer. Okay, so what's the answer? 6 point. Good. Okay. Perfect. So it's pretty much the same. So this is the sodium. This is about 23 gram per mole. Hydrogen is about 1. Carbon is 12. Oxygen is 16, but you have a 3. Okay, so it's multiplied by 3. So if you add them all together, it will be 84. Is that 84? Yeah, 84. So then you just need to divide 508 grams over 84, which is your formula weight of your sodium bicarbonate. So if you look at this one, the grams will cancel top and bottom. You get the numbers in moles by just doing this over there. Okay, so 508 divided by 84 gives you your answer right there. Because it tells you how many grams it weighs per moles, but this is your actual mass of it. So you get the numbers. Okay. Makes sense, right? Just the actual mass divided by molecular weight or formula weight will give you number in moles. That's it. But make sure you guys do count the numbers of each element in the formula so you can get the right number for the formula weight or molecular weight. And divide that actual mass by that so you can get the number. All right. All right. So we have another review on Monday. So I hope you guys study those over weekends. And if you have any questions over the weekend, just bring the questions on Monday so we can do it together. That's also a good way to study for the exam. But anyway, you guys are doing great so far. Okay, very good. Oh, so if you have those okay. Okay, you need to tell me which one is combination reactions, which one is decomposition, or which one is a combustion reaction. I'll give you 1 minute. I don't think it's balanced either, but you know, you can also try to balance the equation. That's good. Yeah. So tell me which one is combination or decomposition or combustion reaction. Okay. Give it about 1 minute. Okay, so how about this one? What is this? Combination, perfect. You see A and B combined to be one. So it's combined together, right? So it's combination, right? So it'll be, okay, right? Makes sense, right? How about the second one? Combustion, perfect. Because this is methane react with the oxygen that makes that carbon dioxide and water. So this is a good example of combustion reaction here. Okay, that will be two. Okay. So then, how about this one? Obviously, decomposition, because this is not one, break into two. Okay, so that is the good example of decomposition. So make sure you guys know how to distinguish each chemical equation and what type of a reaction that is in three categories, like combination or decomposition or combustion. Okay. Make sense, right? Can I move on?
So what's the
Yeah.
classification for a combustion?
Huh?
How do you identify combustion?
So combustion reaction is a bit tricky, but combination is the two things combined to make one. But the combustion reaction is the limitation is you're only going to see that something X element interact with the oxygen. Then they'll make something X oxide as a result of it. So that will be quite clear if you look for the oxide on the other. And there are more than one. That was a very good question actually. I do understand the combustion combination looks very similar. But I promise you on the exam, it will be very distinguishable if you just know how to define them. Okay? Sounds good, right?
Yeah.
All right. Good question. So make sure you guys have any question, just ask me, okay? It means you have a better chance to do well in the exam, okay? Or you can also stop by my office, so I can. So if you have those choices here, mass, volume, color, okay? Those three. And I want you to tell me which one is quantitative and which one is qualitative data. So those are three physical property of matter, but you can say, oh, this is the quantitative and the other ones are qualitative. Maybe 1 minute. Quantitative and qualitative, like a quality, like quantity. Yeah. Okay. This is kind of long trip because we talked about this like a second lecture, so it will be a good reminder for the exam. So, what do you guys think about the mass? Is it quantitative or qualitative? Quantitative, okay? This is quantitative because so quantitative means this one. Whenever you have one metal chunk, okay? You have one metal chunk and you weighed it about, on the scale, it was weighed about like a 20 grams, okay? And you add one more chunk of the metal, same metal, on the scale. And then your mass of the metal chunk double, like 20 grams. So when you add more numbers of something that change your data, that's quantitative data. Makes sense, right? So that is why mass is also a good example of quantitative data. But if you look at the color, even though you have 20 grams of metal, or 10 grams of metal, or 1 gram of metal, the color of metal will still stay the same, right? It doesn't matter how much you have of that same material. It just stays the same. It only depends on its quality. So the color is qualitative data. So if you change the quantity of this material, that change your measurements, that's quantitative data. If it doesn't, it's qualitative, okay? So for example, The volume, how about volume? Is it quantitative or quantitative? Perfect. Because if you add more and more, you need to have a bigger and bigger space. So that is for sure quantitative data. Volume is quantitative. How about next one? Texture. Qualitative, perfect. Because the texture of something still be same. Even though you have 2 grams, 10 grams, or 100 grams, it's still the same. Makes sense, right? Good job. Okay, the next one. Okay, so if I give you okay, there's an element with a charge, and there's other elements with a charge, and it was a positive and negative. Okay? And if we have a compound out of these two, what's the name of this one? Ionic compound. That's the answer. You already got it right. That's good. So cation, and so the ionic compound means this one. Ionic compounds mean you have a metal cation, which is positively charged, and they're going to interact with the non-metal, which is not metal, anion. So anion means that has negative charge. So as you know, if there's something positive or something negative, they're going to have some electronical interactions, because plus and minus. They follow the Coulomb's law. They'll have some interaction there, and they form some compound. We call them ionic compounds. Okay. So the one we talked before was sodium chloride. Okay. Sodium is metal, but it will become cation when it's ionized. And this chlorine is anion, and also non-metal, which is on the right side of the periodic table. So most of the left ones, the one on the left and the bottom is what? Metals in your periodic table. Most of the right and the top corner, they'll be mostly non-metal, and some in between, we call them metalloid, like silicon, which we use as a semiconductor for making microchips. Okay, so makes sense, right? Okay, so for example, if you have a non-metal bound to non-metal, like N2O5, what compound is this one? Is it ionic compound? No, it's a molecular compound. Okay, because these two are both non-metal. Then it's not ionic compounds, it's a molecular compound. Okay, okay, let's move on. Okay, here's the thing. If I say iron is rusted in water, and tell me if it's the chemical change or physical change. Chemical change, perfect. Because the rusted, when iron become rusted, that it is not iron anymore. It's iron oxide. So it will actually change its chemical formula, chemical composition of starting material. So then that will become your chemical change. But how about this one though? If you have seawater is being vaporized, this will be a good example of what? Instead, physical change. Perfect. Physical change. Great. So, meaning when the water is vaporized, now the H2O in gas phase, but there will be still H2O. So H2O in liquid phase to the gas phase, it only shows you the phase transition, but didn't show you the change in chemical formula, which is still same H2O. So it's a physical change. Makes sense, right? Good. All right. The next one. This is pretty easy one. Okay. So if you have this number, can you guys tell me how many suffixes are there in this number? It will be 1, 2, 3, 4, 5, 6, 7. Perfect, 7. So in here, even though they're 0-digit numbers, if it's in the non-zero digit number, like 1 here and here, you count them also as a suffix. But if you have the 0-digit numbers are not surrounded by non-zero digit number, and you don't count them normally, just 3 over here. But if they're inside, you count them all as a suffix. Okay? Do you guys remember this? It's a long trick, right? This is what we discussed before. But make sure you guys know how to distinguish them. The best way to put this in the how many suffixes in this number is a scientific notation. You can do this one is okay. So maybe here's a hidden decimal point. 1, 2, 3, 4, 5, 6, right? So then we tend to 6. This is the same number. But in this way, it's actually much easier and clear for the readers for reading this number, as there are only 3 suffixes. Because as I've said before, in this case, it could be 3 for sure, but 4 and 5 and 6 and 7. But normally it's just 3. But to make sure there's only 3 suffixes, you can use a scientific notation instead. It is much easier and for us to read and analyze. Because we know for sure there are only 3 suffixes in this number. Okay, how about this one? So if you have how many suffixes here? So we don't count them here. So if that is less than 1, we only count the one that is non-zero digit number, and we don't have to worry about those. So it'll be 3. And same here. If you have a 0, 0, 7, 0, 2, it's still 3. Okay. Yeah, I think that's what I have today. But do you wanna do one more, maybe? Just anything? I'll do maybe here. I don't know if you guys remember this. If you have carbon is positively charged, can you guys count the numbers of protons and neutrons and the electrons by looking at the carbon elements in periodic table? So this is atomic number 6, and this is the mass number, atomic mass number. Then you'll be able to know how many protons and neutrons and electrons are there with this 1 plus 4 charge. Okay, about 1 minute, and we can do this together. And let's have some time for the extra credit. All right. Okay, so if you look at this one over here, atomic number, once again, same as numbers of protons, so it'll be just 6 there. Atomic mass number is the proton number of proton plus numbers of neutrons. So that's 20, so that's 12, but you have a 6 proton there, so that makes 12 minus 6 will be 6. So that makes 6 proton, 6 neutron makes 12 over here in the atomic mass number. Okay, and then, but the thing is, this one positively charged, meaning you're missing 1 electron. So you have 6 proton, which is positively charged, but you only had 5 of them, so that's why it's positively charged. If there was a 6, it could have been just neutral, and so it would be 0 here. But it's 1 plus charge because it has 1 more proton than the numbers of electrons, which is 6 and 5. So if it was 7 instead, it could have been negative carbon over there. Because you have more than what you have for the protons. So because the electron is what? Negatively charged. Okay. Makes sense, right? We good? Are we good? Okay. All right. Thank you guys. That's it for today. Let's